All right, so just so that we are clear, what is the difference between an electron configuration and an orbital diagram? What's the difference? Because on a test, if I ask for the configuration, you want to write the configuration. If I ask for the orbital diagram, if you forget the boxes, obviously that's not going to help you on that question. So what's the difference between an electron configuration and an orbital diagram? A diagram infers what? Christian? A diagram. Yeah, some sort of picture or graph. So what would be represented by a picture or a graph up here? It would be the boxes, yeah. Now, we can't just have a bunch of naked boxes up here. So it's really, the orbital diagram is the picture that goes along with the electron configuration. So the electron configuration is kind of the zip code for the electrons. It's the location of all the electrons, or if you're going to use the shortcut, for the outermost electrons. So the electron configuration, if it is the shortcut, would have a noble gas, and then it has a bunch of numbers and letters and exponents telling you where electrons are located. The orbital diagram adds the boxes to accompany that. So it's a more detailed model or version of the electron configuration. Any questions on that? All right, so let's take a look at 1A. So the shortcut would be argon, which has 18 electrons. Add on the 4s1, that's where the potassium would have its 19 electrons. And who can tell me why 4s only gets one box? 4s, why is it just one box? Why not two boxes? Why not 7 boxes? Oh, yeah? It is the first one. What shape does an s orbital have? If I say an s orbital, it would look like a what? The electron wave around the nucleus, does it look like a sphere, a peanut, a daisy petal, or a fancy flower petal? An s orbital. Andrew? It would be a sphere. So I had some people asking, well, how do you do the boxes? How do you know how many boxes you have? It all goes back to this picture right here. You're always going to have an odd number of boxes. Why? Because the number of orbitals, whether it's S, P, D, or F, it's always an odd number. S has one box, one shape. P gets 3 boxes because it's 3 shapes. D gets 5 boxes because it's 5 different shapes. And F gets 7 boxes because it's 1, 2, 3, 4, 5, 6, 7 different shapes. Questions on that? You always have to have an odd number of boxes. Quick show of fingers. How many electrons can you put in a box? Yeah, see a lot of 2s out there, right? 2 electrons in a box. And if you have 2 electrons in a box, Brady, what has to be true about that? Yeah, one has to be a positive 1/2, one is a negative 1/2. What do we mean by that? It would be opposite spin. So like a half arrow up versus a half arrow down. So that would be 1A. Question 2A. For cobalt, rather than listing out all 27 electrons, again, we'll start out with argon. And then we go 4s2, 3d7. S gets 1 box. D gets 1, 2, 3, 4, 5 boxes. And again, it is Hund's rule that says you put the 7 electrons in there individually. 1, 2, 3, 4, 5. Now you go back, paired up 6 and 7. And because of this picture, there's 1, 2, 3 electrons without a partner. Any questions on 2A? All right, 3A, we're not going to list out all 14 electrons. So for silicon, you go backwards to neon. That tells you where 10 of the electrons are located. And then we just need the last 4. So 3s2, 3p2. S gets 1 box, P gets 3 boxes. And again, it goes, some people drive fast. S, P, D, F. And it goes 1, 3, 5, 7, because they have to be odd numbers. Any questions how we got 3s2, 3p2? All right, and then 4A. Now, technically, this isn't really a shortcut, because bracket HE bracket would be 4 keystrokes. Simply, you could just do 1S2, and that would be 3 keystrokes. So it is a shortcut, but it's not really a shortcut. But anyways, this would be the noble gas configuration shortcut. 1 box for the 2s orbital with 1 electron. It's got 1 unpaired electron. Quick show of fingers. How many of those 4 did we get right? Okay. Looks okay. I see some mixed reviews. Quick conversation in your small group. If you got some of these wrong, where did you go wrong, and what do you need to do to fix these? Quick conversation. All right, back as a whole group, so that we do really well on Thursday's quiz, which with the end of the marking period being Friday, that's going to be basically the first assignment on the 3rd marking period. So to start out the 3rd marking period with a good score, what do we need to do to fix any of these? Do you have any leftover questions? Shortcut, boxes, half arrows, questions? All right, let's go ahead and take a look at 6A. You didn't have to do number 5. There was no A. But 6A, you would get xenon, 6S2, 4F14. You got to hop down to row 4. Well, the 4F group, go all the way across. That would be 14. Bring it back up to 5D7. So S gets 1 box, F gets 7 boxes, D gets 5 boxes. You're going to put them in there individually first. Go back, pair up number 6, pair up number 7. This right here is what tells you you have 3 unpaired electrons. Again, if you're wondering why we care about unpaired electrons, that has something to do with the magnetic properties of that element. You wouldn't really get to that until you get to AP chemistry, but that's talking about paramagnetism, diamagnetism, and you actually can measure for that in the lab.
What do the boxes represent? Like underneath?
Rather than drawing all the crazy shapes, S, P, D, F orbitals, the boxes is an easy way to represent one of those orbitals.
Okay, so what are the slashes inside the box?
Those represent the electrons in those orbitals. So it's a half slash up or a positive, like 1/2 arrow. That means there's an electron with a positive 1/2 spin in that orbital. If you're going to put a second electron in this orbital or box, it would have to have a negative 1/2 spin. Now, again, it's not as easy as saying like a basketball is spinning in one direction versus spinning in the other direction. It's more of a mathematical concept, but it does deal with the spin of the electron, which can be measured as far as magnetism is concerned. So boxes represent shapes, and the arrows represent the electrons in those shapes, which are called orbitals. Good to go? Sweet. All right, so that was 6A. Let's take a look at 8A. You didn't have to do 7. So for selenium, which is element 34, we don't have to list all 34 electrons. If we start with argon in parentheses, that takes into account 18 of those electrons. So then we just need to finish it from there. 4s2, 3d10, 4p4. The S, or spherical orbital, there's only one way to draw that, so that's 1 box. The d orbitals, there's 4 4-leaf clovers plus a hula hoop version, so that's why there's 5 boxes. And P, there's only 3 ways to draw that peanut in X, Y, Z dimensions. So you get 1, 2, 3 boxes. 4 electrons, put them in there individually first. Go back, pair it up. That gives you 2 unpaired electrons. Questions on that? Okay. Would you agree 6s2, you have to put 2 electrons in one box? Okay. Was the question about the 4s, 7 boxes? No, it was more so the d's. Okay, so would you agree you have 5 boxes for all the d's? Anytime you see a d, there's 5 boxes. And with 7 electrons, would you agree the last rule we did was Hund's rule? You got to put electrons in there individually. 1, 2, 3, 4, 5. You'll go back paired up number 6 with an opposite spin, 7 with an opposite spin. So in other words, you could pair them all up from the beginning, 1, 2, 3, 4, 5, 6, and 7, but that would break Hund's rule. Electrons don't want to be in the same box because they both have a negative 1 charge. So you want to put them as far apart as possible. They'll go in the same box if they have to, but it's all based on that opposite 1/2 spin. There you go, Hund's rule. So there's really only 3 rules to doing this. The Aufbau principle, you start at energy level 1 and work your way up, unless you're going to start with the shortcut. That still follows the Aufbau principle. Number 2, the Pauli exclusion principle. You can only put 2 electrons in the same box. They have to have opposite spins. And then Hund's rule, because electrons are all negative, Hund's rule says you got to put them in there individually before you go back and pair them up. That's how you do electron configurations. 3 rules. Now, again, it's a little bit more complicated than all of that. There's quantum mechanics and all that sort of stuff, but we don't have to worry about quantum numbers. If you follow those 3 simple rules, you'll get pretty much any question right. Questions on those 2? All right, let's take a look at 9a. There's no way you'd want to list out all 83 electrons for bismuth. So if you start with xenon, which is element 54, then you can just finish it from there. Go down to row 6, the S group, so 6s2. And then you're going to hop down to the bottom of the periodic table, 4f14. Then you'll hop back up to 5d10, and you'll wrap it up with 6p3. Again, we don't have any paired electrons here because you'd rather put those 3 electrons in individually. So because of that, we have 3 unpaired electrons, all because of Hund's rule. All right, number 10 for cadmium. Rather than starting out with all 48 electrons, we can start with krypton, which basically is the shortcut to say, hey, here's 36 electrons. We don't really care about them. And then we'll pick it up with 5s2, 4d10. Now, in this case, there's 0 unpaired electrons. Because the s orbital is filled, because the d orbitals are filled, there's no electrons that don't have a buddy. So there'd be 0 unpaired electrons. And in AP chemistry, the vocab word for that, 0 unpaired electrons, all electrons are paired up would be diamagnetic. So that would have some sort of magnetic property. If you pour like nitrogen, the nitrogen we breathe, N2, if you would liquefy that and pour it through a magnet, it would pass right through. It would rather die than be in a magnetic field, so diamagnetic. That's not where we get the word diamagnetic, but it's a cute little trick to help you remember that. All right, any questions up through 11? All right, well, I guess we didn't have to do 11. Yeah, 12A and 13A. All right, so 12A would be neon, 3s2, 3p4. There's 2 unpaired electrons right there. And 13A would be xenon. Drop down to row 6, 6s2. Hop down to row 4f14, all the way filled up. And then hop back up to 5d10, all the way filled up. So, one more conversation. What did you do well on this, and what needs cleared up before Thursday's quiz? Quick conversation.
Because of the number, so not always 10 for like 9.
First number is not for loser. The letter decides how many boxes you have. You just have to fill each box with that number. Up to that number. So you start from
All right, back as a whole group. Jaden, you had a question.
What determines the amount of boxes you use? Because I saw that the three right there for 3 people is 3 boxes, and then 4 has that 4 slots. But the 3S2 only has 1 box. It doesn't have
Right, so the energy level tells you how big that box is. So again, you really have to know your 4 shapes. S would be what shape? It's a sphere. Okay, it could be a really small sphere, a 1S sphere. It could be a bigger sphere, a 2S sphere. It could be a bigger sphere, a 3S sphere. And if you're all the way down at the bottom of the periodic table, it could be a 7S sphere. So the principal quantum number just tells you how big the orbital is. The letter tells you what shape it is. How many different ways can you draw a sphere? Spin it in all 3 dimensions. Would it look any different? No, it's one shape, one box. The P shape is what shape? The peanut. How many dimensions are there? If you're a cartoon, you live in a 2-dimensional world. 3. So there's an X P orbital, there's a Y P orbital, and then in 3 dimensions, there's a Z P orbital. So if you go back to that slide that I just put up here, there's 3 different pictures for the P orbitals. So that's why there's 3 different boxes. What do the D orbitals look like? Yeah, kind of like the 4-leaf clover. Now that doesn't start out with a D, so I call them daisy petals. But yeah, it looks more like a 4-leaf clover. There's 4 of those pictures. And then don't forget the 5th one. It's kind of the crazy one that has the hula hoop around its waist. So because there's 5 different of those 4-leaf clover shapes, that's why D's always get 5 boxes. It doesn't matter if it's a small 4-leaf clover, which would be the 3D orbital, or a really big 3, 4. It could be a 6D orbital, a really big 4-leaf clover. But again, that doesn't change its shape or how many boxes you get. Does that make sense? Your only options for the number of boxes will ever be 1, 3, 5, or 7. It's kind of odd, isn't it? It's literally odd.
Yeah, where did the 7 come from?
The 7? The F's. So those are the fancy flower petals. There's 7 of those different shapes. Does that make sense? Perfect. The 4F goes before the D. If we go back to our periodic table, so here would be 6S. After element 56, I have an arrow pointing you down to here. You go down to the F section. And then after 70, you'll hop back up here and go back to the D section. Now, are there some exceptions here? Yes. So in some cases, you might actually kind of go here first and then hop down, but you don't have to worry about any of those exceptions. Basically, the only exceptions you have to worry about would be the D4s or the D9s. I'm never going to put one of these elements on a test or a quiz because there's not enough data to support why you would do that. It's just this is what the atom does, and therefore there are exceptions, and you would just have to memorize them. But again, that's way beyond the scope of this class. Yep. Other questions? Leftover questions. All right, so to review everything that we've done so far, I want to play our electron configuration polka one more time. And then I want you to listen for, in like verse 3 and 4, it brings up a special type of electron. And I want you to write down in your small groups, what are those electrons called and why are they so special? That's the last concept for this half of the unit.
There's a little game that's as easy as can be, with numbers and letters and lots of chemistry. It comes from quantum theory and wave mechanics stuff. But for now, just learn the game, and that will be enough. O1S2, 2S2, then comes 2P6. The electron configuration game is really slick. From alkali to halogen and on to no gas. Now you can understand the periodic law at last. Well, atoms have orbitals where electrons like to play, and those electrons fill the orbitals in a special way. It's a building up process, you can learn it in a second, and you can call it Aufbau if Deutsch is what you sprechen. 1s2, 2s2, then comes 2p6. The electron configuration game is really slick. From alkali to halogen and on to noble gas. Now you can understand the periodic law at last. Well, the outermost electrons
Oh, here we go.
in atoms have three. The most important ones for understanding chemistry. These valence electrons are shared or lost or gained in chemical reactions when atoms rearrange. And 1s2 and 2s2 and then comes 2p6. The electron configuration game is really slick. From alkali to halogen and on to noble gas. Now you can understand the periodic law at last. But the joy is that now, at this point in history, we can finally solve the periodic table mystery. Why do elements form families? What is the explanation? Their valence electrons have the same configuration. Then 1s2 and 2s2 and then comes 2p6. The electron configuration game is really slick. From alkali to halogen on to noble gas. Now you can understand the periodic law at last.
So, quick conversation in your small group. It deals with today's essential question. What are the special electrons in an atom called? Why do we care about them so much? Where are we going to go when we go to the next slide? So, quick conversation. All right, what are these special electrons called? The ones that we really care about. Starts with a V. Oh yeah? Valence electrons. And why do we care so much about valence electrons? What makes them special? Yeah, they're going to be the electron's next unit that we're going to use to form bonds with other elements. And why are they called the bonding electrons? Are they on the inside of the atom or the outside of the atom? They're the outside of the atom. So basically, we can just kind of ignore all the core electrons, the electrons in the inner shells, and we can really just focus on those outer electrons. So what is a valence electron? They are the outermost electrons, which are used to form bonds with other elements. So you want to turn in your slideshow to this slide right here. They're the electrons in the highest energy level. That's why they're in the outermost shell. It should be somewhere around slide 32 in your slideshow. Chance, what does yours say there? If you look at that slide.
Page 15.
On page 15, but on your slideshow, does you have a little number in the bottom?
21.
Oh, 21. Ooh, I might have to go back and read them. So maybe slide 21. So the nice thing with our shortcut is, obviously, the valence electrons won't be in any of those inside electrons. So what's the highest energy level for lithium? Energy level 1, 2, 3, 4, 5, 6, or 7. Energy level 2, correct? This right here. And how many electrons do I have in energy level 2? Well, that right there tells me we have 1. If we take a look at beryllium, the highest energy level is 2. And how many electrons do we have in energy level 2? There would be 2 valence electrons. Oh, we're going to mix it up a little bit. S versus P. Which is bigger, energy level 2 or energy level 2? They're the same. I have to count all of the electrons in energy level 2. So because energy level 2 is my highest energy level, if I add 2 and 1 together, there'd be 3 valence electrons. Carbon would have 4 valence electrons in energy level 2. Nitrogen would have 5 valence electrons in energy level 2. Oxygen would have 6 electrons in energy level 2. Fluorine would have 7 electrons in energy level 2. And neon would have 8 electrons in energy level 2. Any questions how we got that? The electrons in the highest energy level. How many valence electrons would potassium have? Quick show of fingers. Just careful. Try to be respectful here. How many valence electrons would potassium have? We'll just have 1. It would happen to be in energy level 4, but yeah, it has 1 valence electron. What about calcium? How many valence electrons? Yeah, 2. Those 2 electrons happen to be in energy level 4, but yeah, there's 2 valence electrons. All right, if we take a look, we're going to skip some elements. You'll see why in a second. We're kind of leaving out the middle of the periodic table there. But let's hop all the way over to element 31, gallium. Which is the highest energy level? Energy level 4 or energy level 3? Energy level 4. And this says valence electrons are the electrons in the highest energy level. So we're only going to count energy level 4 electrons. How many valence electrons would gallium have? 3. There you go. Germanium would have 4. 2 plus 2 would be 4. Arsenic would have 5, then 6, then 7, then 8. Take a look at those answers we just came up with. Look at the periodic table and discuss the trend that we just developed. If you don't ever want to have to do all of this math again, how could you just look at the periodic table and identify how many valence electrons an atom has? What's the pattern? Lithium had 1 valence electron. Potassium had 1 valence electron. How many do you think sodium would have? How many do you think rubidium would have? What about francium? They have 1 valence electron because the song said they have the same electron configuration. Now, this is technically 1s1, 2s1, 3s1, 4s1, 5s1, 7s1. The energy level is different, but they all end with S1. They have 1 valence electron. Anything in column 2 would have how many valence electrons? 2. They're all like 2s2, 3s2, 4s2, 5s2, 7s2. They're all S2 configurations. Again, we're skipping the middle of the periodic table. Boron, aluminum, and gallium all had how many valence electrons? S2, P1. Put that together, 3 valence electrons. Now, it's not in column 3. You'll just have to use the last digit of the column number. So column 13, because they're all S2, P1 configurations, it'll always be 3 valence electrons. And then 4, then 5, then 6, then 7. Column 18 would have 8 valence electrons. Questions on that? You'll never have to look at all the S's and P's again. You simply look at the column number. Throughout question.
Didn't helium only have 1 valence electron?
Oh, yeah, let's talk about helium. Quick conversation in your small group. Just when you come up with something that's easy, a pattern to remember, there's always exceptions. Quick conversation. What is the configuration for helium, and how many valence electrons would it really have? Column 18 makes you think it should have 8 valence electrons. But how many electrons does helium actually own? 2. Can you have 8 outer electrons if you only have 2 electrons in the periodic table? No, it's simply a 1s2 configuration. So therefore, helium would be an exception. Helium would only have 2 valence electrons. So that's sometimes why you'll see helium located here, because it is a noble gas, but sometimes you'll also see it located kind of in an outline fashion right here, because it does sometimes act like those elements because it is an S2 configuration. Good point. Questions on that? Now, all along, we've been saying the Ds are kind of weird. So let's talk about the Ds. Technically, valence electrons should be the electrons in the highest energy level. But for transition elements, the S's and the D's are so close in energy, we really just oftentimes lump them together. I realize energy level 3 is less than energy level 4, but because it's a d orbital, that's a super high energy level 3, and S is a super low energy level 4. So when you really compare them, they're almost the same. That's why the D's kind of act weird. We'll lump them together. That would be 3 valence electrons. I know it kind of breaks the rule, but that's just how the D's behave. For titanium, you'll take a look here. You'll think that it has 4. So when you look at your periodic table, if you look under scandium, sure enough, it shows that when it does form an ion, when it loses its valence electrons, it becomes a +3 ion. Why? Because it has 3 valence electrons. When you take a look at titanium, when it loses its valence electrons, you'll notice it has some options there. It could lose 2 valence electrons, 3 valence electrons, or the periodic table says it could lose 4. Because 4 is the bolded answer, that's the most common answer. But we'll go with 4. When you take a look at vanadium, it could be a 5. But I put a question mark there. Let's check and see what the periodic table says. Vanadium could be a +3, a +4, or a +5 ion. So it could lose 3, 4, or 5 valence electrons. When you look at the bold option, it says it's only 3. So we'll just cross it out and say 3. Why? Because that's what the periodic table says. Chromium, could we lump all of these electrons together? Sure. So you might think it has 6, but I put a question mark there and see what the periodic table says.
So you just add them together and always check the periodic.
You just check the periodic table. Yep. So if you look at chromium, +6, 6 valence electrons is an option, but it's not the most common option. It would be a +3. So you just cross it out and say 3 valence electrons. If you look at manganese, could it have 7 valence electrons? Sure, but that's probably going to be pretty rare. So I put a question mark there. Let's look at what manganese says. Notice +7 valence electrons is an option, but it's way more common for a +2. So just cross it out and write 2. So by the middle of the D section, we're basically just back to counting the highest energy level electrons. Let's take a look at iron. 2, 3, or 6 are options. 3 is the most common option. Cobalt, 2 or 3 are options. These 2 right here are going to be the most common options. If you look at nickel, there's no way it's going to have 10 valence electrons. So when you look at nickel, it could be 2 or 3. 2 is the most common option. If you look at copper, 1 or 2 could be an option. 2 is the most common option. So we'll take this 1 electron and one of these right there. So 2 valence electrons. And for zinc, it's 1 or 2. 2 is the most common answer. So really, the D's are weird, but you don't even have to memorize them. You simply look at the periodic table, look at the most common bolded option. Questions on that? All right, so I was hoping we would have time for this example right here. We're not going to have time for tellurium in class. So what I would like you to do is wrap this one up for homework, and I'll check that one tomorrow, tellurium. It says something about a practice quiz there. I can probably give you some time in class to work on that practice quiz to get ready for Thursday's actual quiz. So as long as you do this slide, the shortcut electron configuration, the orbital diagram that goes along with that, and how many valence electrons tellurium has, we'll check that tomorrow. Sound good? Sweet, nice job today.